Today I'm going to talk about pulse modulation and how it helps in digital communication. In modern system, we need to convert analog signal to digital because it makes transmission and storage much more efficient. Pulse modulation is a technique where we change the characteristic of a pulse train based on the analog signal. It plays a key role in converting analog signals into digital format. There are few common types of modulation technique, which is pulse code modulation (PCM), pulse wave modulation (PWM), and delta modulation (DM). Among all these techniques, PCM is the most widely used. It offers strong resistance to noise, works well with digital storage, and keeps the signal quality stable even over long distance. PCM works through three main steps. First, we sample the signal, then we quantize it, and finally, we encode it into binary form. PCM is essential for today's technology, including voice over IP, cloud computing, and online streaming. That's why it is such an important part of modern communication system. The purpose of our study is to stimulate and analyze PCM using MATLAB. We also compare PCM with PWM and DM to see how each one performs under real signal conditions. This helps us understand both the theory and practical benefits of PCM.
So how PCM will works? PCM will convert analog signal into digital signal. It uses three steps. First step is sampling. It will take in measurement of the signal at regular intervals. Second is quantization. It's rounding each sample to the nearest value. The last is encoding. It will turning values into binary, which is zeros and one only. A low-pass filter will remove unwanted high frequency before sampling. The signal is sent digitally and reconverted to analog at the receiver. In real-life application, PCM will use in phone system, CDs, digital music, TV, video calls, data storage, space, and satellite communication. So how pulse width modulation (PWM) will works? PWM changes the width of pulses to represent an analog signal. A comparator compares a changing RAM signal with the input signal, and the pulse gets wider when the input is stronger and narrower when it's weaker. In real-life application, PWM will use in motor speed control, LED brightness control, and the power delivery to devices like heaters and amplifier. It also creating AC signal from DC power. And the last is microcontrollers to create analog-like signal from digital output. How data modulation (DM) works. So DM sends only the change in signal, not full values. It uses just one bit, one meaning signal went up and zero signal went down. It builds a staircase-like version of the original signal, and it works best with fast sampling. So it used in voice transmission, remote sensor, but it can have problems like slow overload, granular noise, and adaptive DM. This table is comparison between PCM, PWM, and DM. The advantage for PCM is high quality and accuracy, and it also great for digital system. For PWM, it's good for power control, simple and efficient. And DM is simple and it uses less bandwidth. Disadvantage for PCM is needs high bandwidth and also it's complex circuits. But PWM is less accurate, needs filtering, and it has much noise. For DM, it has lower quality and it has slow overload.
The main objective of this project is to simulate and analyze a PCM system using MATLAB. To do this, we use a sine wave as the analog input signal. A sine wave is a simple and clear signal, which makes it easier to show how PCM works. We chose PCM for three main reasons. First, it gives high signal quality and strong resistance to noise. Second, it is widely used in real communication system. And third, it is easier to stimulate and analyze compared to other techniques. This is the simulation setup we use for our PCM system. Here are the main steps in the PCM process. First, sampling. We take values from the analog signal at regular interval. Second, quantization. We round each sample to the nearest of 16 levels. Third, encoding. Each level is turned into a 4-bit binary number. Fourth, decoding. We convert the binary back into the quantized value. Finally, reconstruction. We rebuild the signal using the stars function and zero-order hold.
So this is the MATLAB code that I use for the PCM. And first, I define the parameters for my simulations. So Fs is the sampling frequency set to 8,000 Hz. Fm is the frequency of the input sine wave, which is 100 Hz, and the durations of the signal is 0.05 seconds. Bits equals to 4 means that I'm using the 4-bit quantizations, which give us 16 quantizations levels. Then I created the time vector t and the analog x using a sine functions. Next, from the line 12 to 19 is for the analog signal. Um, this shows the original sine wave before any processing. I use the red line to represent the continuous waveform over time. So from line 21 to 29 is for the graph 2, which is for the sample signal. Here I sampled the sine wave at 8,000 Hz, so each dot represents one sample. So I use them to show these individual samples using points clearly. Next, on line 31 until 43 is the third subplot shows the quantized signal. So using 4 bits, I calculated the quantization level as 16 using the formula 2 power of n, which is equals to 16. So each sample value is rounded to the nearest level using floor and adjust with step size. Then I plotted the quantized values using stairs function to show the stepwise nature of quantization. Finally, for the fourth graph, which from line 45 until 56, compares the original analog signal with the quantized version. So the red dashed line is the original and the blue stairs represents the quantized versions. This visualizes how close or far the quantized signal is from the original. So I use the legend function to label them clearly. So this is the result for the pulse code modulations PCM using the MATLAB code. Starting with the first graph. So this is the analog input signal that's shown as smooth sine wave. It represents a continuous signal like sound or voltage. So our goal in PCM is to convert this into a digital signal without losing too much information. Next, for the second graph, we have the sample signal. Here, the analog wave is sampled at the regular time intervals. So, this vertical line shows the sample points, and the sampling must follow the Nyquist theorem, meaning that we must sample at least twice the highest signal frequency to avoid the distortion. Moving on to the next graph, from the first image, this graph shows the quantized signal. and each sample value is rounded to the nearest level. So this is called as quantizations. And it simplifies the signal but also introduces quantization noise, the small error that occurs due to rounding. Lastly is the comparisons between the original signal in red line and the reconstructed signal in blue line. As you can see that the reconstructed signal follows the original shape quite well, even though it's not perfectly. This shows that PCM can digitize analog signal efficiently, preserving the overall waveform while simplifying it for digital transmissions. To conclude that PCM involves sampling, quantizations, and encoding, and it's widely used in digital audio, telecommunications, and data storage. Despite some small errors, it's a very effective method for converting analog to digital.
Hi, I'm Hazika Hasbi, matrix number 97732, and I'm going to talk about our performance analysis. So, in our MATLAB based pulse code modulation simulation, we analyze the system based on the signal accuracy, noise behavior, and overall transmission quality. So as you can see at the result shows that the reconstruct signal maintains high fidelity when compared to the original analog input. And then although there is some slight distortion, the key features of the original waveform are well preserved. And then this is because the sampling rate used in the simulation is slightly higher than twice the highest frequency component of the signal, which is essential for accurate signal reconstruction, and that this to ensure that all necessary information from the original signal is captured during the sampling. And then, additionally, our simulation used a relatively high quantization resolution, which help minimize the distortion. So the smoother the reconstructed signal, the better the quantization accuracy. So, and then that's what we observe. In short, proper sampling combined with a finer quantization level result in a more faithful signal reconstruction. So when it comes to optimization suggestion, based on our observation, there are two main ways to optimize the performance of our PCM system. First is increasing the number of the quantization level, and then the second one is we consider increasing the sampling rate. So for the first ways to optimize our PCM system is we can increase the number of the quantization level or bits per sample. In our simulation, we notice a stair-stepping effect in certain part of the signal, especially when the waveform changes smoothly. This is the result of the quantization noise caused by limited bit resolution. By using more bits, we can reduce this distortion and achieve a signal that is even closer to the original. The second ways of optimization our PCM system is we consider increasing the sampling rate when working with more complex or dynamic signal. Although our chosen rate of 8,000 Hz perform well for the test signal, a higher sampling rate could provide a better detail and accuracy for a signal with a rapid changes. So overall, both adjustment, which is increasing the quantization level and using a higher sampling rate, will enhance the system performance and produce more accurate results.
The conclusion is MATLAB is used to design and simulate a PCM system. The simulation showed that PCM effectively converts analog signals to digital with high accuracy. PCM offers excellent signal quality, making it ideal for audio, phone, and satellite communication. However, it requires more bandwidth and complex processing compared to simpler methods like delta modulation, or also known as DM. Overall, PCM performed well in both clean and noisy conditions, proving its reliability and relevance in modern digital communication.